In 2023, a bug called Zenbleed was found in AMD processors. It lets one program on a machine silently read data belonging to a completely different program. Things like passwords, encryption keys, and anything else in memory could be silently stolen. The bug had been in shipped hardware for years. Nobody caught it because it only triggered under a very specific sequence of speculative execution that no normal tests would generate. This paper presents a tool called Cascade, which takes a new approach to testing CPUs automatically. I'll walk through the background, what was wrong with existing approaches, and what Cascade does differently. Let's start with fuzzing, since that's the foundation everything else is built on. Fuzzing is a testing technique where you can automatically generate large numbers of inputs and feed them into a program, and you can look for cases where things go wrong. The idea is pretty simple. It's sort of like element hunting, where physicists shoot atoms into each other, and eventually those atoms of different elements combine and form a new element, although very rarely. And the idea is essentially the same for fuzzing. If you throw enough random garbage into a program, eventually you'll hit something that the developers didn't anticipate. What makes it practical is that computers can run these test cases extremely fast, often thousands or millions per second, depending how they are made. And you don't need to develop every single edge case manually, and with enough randomization, all those edge cases could probably be found. And you just let the fuzzer explore the program, eventually until you hit a crash or other type of unexpected behavior. Tools like AFL and LibFuzzer uses this idea and have already found a huge number of real security vulnerabilities in different types of programs. It's become a standard part of how software gets tested. The main issue, though, is that CPUs don't just take in inputs like programs do, and they don't produce a standard output the way that programs do. Its behavior depends on instructions that it executes and the internal states of its registers and things like that. Hardware bugs are a distinct category from software bugs, and the consequences tend to be worse, since when a software bug is found, developers can just push a patch to that software. But when a hardware bug is found, that chip has already been manufactured, shipped, and installed in millions of computers, and then options become much more limited, although patches, of course, are still possible. Some prominent examples of hardware bugs are Spectre and Meltdown, which were disclosed in 2018. They exploited the way CPUs perform speculative execution, which is executing instructions ahead of time based on predictions, and that allowed unprivileged code read from kernel memory. Another example is Zenbleed, as mentioned, which was found in 2023, and was a bug about how AMD processors handle a specific register operation during speculative execution, which under the right conditions let registers be read before properly initialized, which leak data to other programs. What these bugs have in common is that they require a specific sequence of operations to trigger. That's what makes it so hard for conventional testing to find. There are two main approaches to verifying that a CPU is correct. The first is formal verification, where you essentially have to make a mathematical proof that the CPU will do exactly as you describe it. You have to write down the properties that the design must satisfy, and then you have to prove that those properties hold true for all possible inputs and all possible execution sequences. The problem with that is scaling, and a full formal verification is extremely expensive and requires a lot of work from a lot of employees. The second approach is fuzzing, which is cheaper and more automated, although does not give you the same exact guarantees that a full formal verification will give you. You generate a lot of test programs and you check the output that it gives you, although there is a chance that not all edge cases are covered. Before getting into the specific problems, let me explain the basic setup for CPU fuzzing, because it involves a few terms that are worth understanding. When a chip is being designed, the design is described in a hardware description language. This description is called the RTL, which stands for Register Transfer Level, which is sort of like the source code of the chip. You can simulate this design in software before it's ever manufactured. This lets you run programs on the design and observe what it does, but in software instead of needing physical hardware. Now, to know whether this simulation is doing the right thing, you need something to compare it against. That reference is called the Instruction Set Simulator, or ISS. An ISS is a software model of what a CPU following a given instruction set is supposed to do. The idea is you run the program on both the RTL simulation and on the ISS, and then you compare the register values at the end, and if they differ, then the hardware design is doing something wrong. This is what is called differential fuzzing. Now, what is one thing that could go wrong with this comparison approach, even if the CPU has a real bug? Well, it's that the bug might not affect the final register values. If a bug causes the wrong computation, but it gets overridden before the program ends, then that final comparison would show no difference, even though something did go wrong. This is one of the reasons that instruction by instruction checking became more common, although that adds its own overhead. This paper focuses on the RISC-V architecture. The RISC-V architecture is an open instruction set architecture, meaning the specifications for how a RISC-V processor should behave is publicly available, and anyone can design a CPU that implements it. This paper tests 6 RISC-V designs: Pico RV32, Kronos, Vex RISC-V, CVA6, Rocket, and Boom. Before getting into what Cascade actually does, it's worth understanding what the paper's authors found when they looked at existing fuzzers on the market. They analyzed DieFuzz RTL and the Huzz, 2 state-of-the-art CPU fuzzers at the time. They developed 2 measurements to analyze the performance of these fuzzers. First, completion. What fraction of the instructions in a generated program actually get executed? The answer for DieFuzz RTL is pretty mediocre, with a median completion rate of about 1.7%. So if you generate a 1,000 instruction program, only around 17 instructions are actually run on average. Second is prevalence. Of the instructions that do run, how many are actually doing randomized fuzzing work versus just setup? For DieFuzz RTL, the median was about 3%. Most of the executed instructions were just initialization code, not the actual fuzzing. So why do you think a random program might fail to execute most of its instructions on a CPU? Well, the reason is control flow, things like branch instructions, comparisons between registers. If register X equals register Y, then it jumps to address Z. It depends on register values that were set by earlier random instructions. These values are unpredictable, so branches often jump to unexpected places, and these fuzzing instructions just never get reached. On top of the throughput problems, there's a separate issue with bug detection. The most thorough approach is to compare the CPU state, meaning all the register values, against the ISS after every single instruction. And if they ever diverge, that means you found a bug at that exact instruction. It's incredibly precise, but it's also incredibly slow. The Huzz reports a runtime overhead of 71%. DieFuzz RTL is sometimes even worse, with an overhead of up to 97%. There's also some practical problems. For some CPUs, identifying exactly which signals in the RTL correspond to which registers isn't always straightforward. And for other CPUs, they might have multiple versions of a register saved at the same time. So to summarize, the problems that occur in existing state-of-the-art fuzzers are that they generate programs that mostly don't execute entirely. They have a lot of initialization overhead, and they also have expensive per instruction checking. And Cascade is designed to address all 3 of these. The key shift in Cascade's design is moving from just mutations to constructing programs. Instead of generating a completely random program, Cascade builds a program where the control flow is decided in advance. A Cascade program is constructed of basic blocks, which are short chunks of instructions, each ending in a jump or a branch. Cascade then decides upfront which path each branch will take, and it then builds a final program so that given the correct register values at each branch point, execution follows exactly the intended path from start to finish. To set those register values correctly, Cascade runs the program through the ISS once during the generation phase, and it collects those values it needs at each branch and uses those to construct the final program. The result of this is that it is guaranteed to complete. This gets the completion from 1.7% from DiFuzz RTL to 100%. Making programs complete solves the throughput problem, but it doesn't solve the detection problem. A program can run all the way to the end and still have computed the wrong values throughout, and you wouldn't know unless you were checking per instruction. That's where entanglement comes in. Cascade links the branch conditions to the results of computations in the program. So if the CPU gets a value wrong, then that next branch goes somewhere it wasn't supposed to, and then Cascade ensures that any unexpected branch leads into an infinite loop. A wrong computation becomes a hang, and then that hang becomes very easy to detect since you can just run that program with a timeout, and if it finishes, that means there's no bug. But if it hangs, then clearly something went wrong. You don't need per instruction state comparisons to be able to see where a program goes wrong. But can you think of a type of bug that might cause this approach to miss? Well, if a bug produces a wrong value but never influences the branch, it will be completely invisible to Cascade. Although entanglement makes this less likely, it's also still very possible. The mechanism that makes Cascade this efficient is what the authors call asymmetric ISA pre-simulation. The straightforward way to build these programs would be to call the ISS every single time you encounter a branch during generation, since you need to know what the register values will be at that point. But that means hundreds of ISS calls per program, one per each branch, which makes it incredibly slow. Instead, Cascade generates a more basic version of each program, where its branch conditions are simplified, and in these versions, the control flow doesn't depend on random data values yet. Cascade thus runs the ISS on this basic version once, collects the register values at every single branch point, and then uses those values to construct the final version of the program, where the branches are now linked to the randomized values. The key part is that the intermediate and final programs have the same control flow and the same values in the register that matter for branching. All that differs is how those values got there. So that means one ISS call is enough to collect everything that Cascade needs. When Cascade finds a bug, the evidence is that the program hangs, it gets stuck in an infinite loop. But the program that triggered it might be thousands of instructions long. That's why Cascade includes an automated reduction step that works in 2 passes. The first pass finds the tail, the last instruction involved in triggering the bug. It does a binary search. If you skip the second half of the program, does it still hang? If yes, then you discard the second half and repeat. Eventually, you narrow it to the specific basic block, and then the specific instruction where the bug expresses itself. The second pass finds the head, which is how far back you need to go to set up the CPU so that the program is in the state to trigger the bug. Cascade searches backwards from the tail to find that earliest instruction that, if removed, makes the bug disappear. And in every case tested in the paper, this process reduced programs down to a single instruction. Cascade was run on 6 RISC-V CPUs for 24 hours, each on 64 cores, and found 37 new bugs across 5 of them, resulting in 28 new common vulnerabilities and exploits. That's more than all prior CPU fuzzers combined. The bugs fall into several categories. 11 are exception handling bugs, which are cases where the CPU either raises an exception it shouldn't or fails to raise one that it should. For example, in Pico RV32, reading certain mandatory CSR addresses causes the CPU to hang completely. And in Kronos, writing to a non-existent CSR succeeds instead of triggering an exception. 12 of these bugs are wrong computation bugs that only appear under the specific conditions and are some of the hardest to find since you need the right sequence of prior instructions to set up. There are also 4 systematic wrong computation bugs, which are ones that produce incorrect output regardless of the microarchitectural state. In Boom, for example, double precision division and square root operations ignore the static rounding mode specified in the instruction and always uses the default mode instead. Cascade also found a bug in Yosis, a popular RTL synthesis tool. When Yosis compiles CVA6's design, it introduces an error that wasn't there before. In terms of coverage, Cascade reaches the same level as NiFuzz RTL 97 times faster, and the same level as the Huzz 28 times faster. Part of this is the higher instruction throughput from programs that actually fully complete. Part of it is the zero overhead detection that makes the fuzzer run much faster, and part of it is the fact that longer programs naturally explore more of the CPU state than shorter programs can. The paper breaks the security implications of the bugs it found into 6 different categories, with bugs often falling into more than one. 12 of these bugs sit in the data flow integrity category, where an attacker sharing the same core can push a victim process into computing wrong results. The boom rounding bug illustrates this. By setting up the right conditions, an attacker can make a victim process use a different rounding model than it actually intends to. 9 of these bugs enable control flow hijacking. CVA6 produces incorrect flags and wrong results in certain floating point situations, which can redirect execution in a victim process. One case shows a missing inexact flag on an overflow that can bypass a security check. In Vex Risk V, there is a related problem where prior instructions can corrupt comparisons, causing 2 equal floating point values to be treated as different. There are also 3 hang bugs across Pico RV32, Chronos, and Vex Risk V that are also all denial of service attacks. The Vex Risk V case is kind of interesting because it's also a speculative execution of illegal instruction that leaves internal resources reserved but never freed, which can cause the CPU to deadlock. And the paper explicitly compares this to the Zenbleed attack. It's also worth being clear about where Cascade can fall short. I think most importantly, Cascade is a Risk V only, and thus only applies to those CPUs. And if it should be needed to be adapted, then it would require a lot of work in order to port them, especially to architectures that have a lot more instructions. And secondly, as mentioned before, the non-termination detection, while it allows Cascade to run much faster, is also a blind spot, as if a bug produces the wrong value but never jumps to a forever loop, then Cascade won't catch it. And although entanglement makes this less likely, it is also still very possible and isn't guaranteed. Although, to be clear, the paper shows that Cascade is also very effective and has found many bugs. To wrap this up, CPU bugs are incredibly real and consequential, and also incredibly difficult to find. With formal verification needing incredibly thorough work and also being very expensive and hard to scale, CPU fuzzing is a very practical alternative, although existing tools have 3 concrete problems, being that of low completion rates, low prevalence of actual fuzzing instructions, and expensive per instruction bug detection. Cascade effectively addresses all 3 of these issues by constructing programs with a predetermined control flow, then entangling that control flow with randomized computations so those wrong jumps become infinite loops, and also using a single ISS run to make constructing these programs more faster. And the automated program reduction also makes finding these bugs much more efficient. This resulted in a total of finding 37 new bugs, 28 new CVEs, and of course, although there are limitations, ultimately it is an incredibly effective and innovative technology for CPU fuzzing.